So I want you guys to help me out here. So how many of you guys know how to bake a cake?
Did you say bake a cake?
Yeah.
Bake a cake,
Yeah.
like from a box.
Yeah.
Yeah.
Okay. Can we say unanimously, everybody here knows how to bake a cake?
I hope so.
Okay.
Mine
Okay,
get burnt all the time.
Good, good. Okay, so now you guys know how to bake a cake. You've been doing it for a while and everything like that. Can you tell me what do I need to bake a cake?
A recipe.
Yes.
The recipe. Well, I want the recipe. Give me the recipe.
Eggs.
Eggs,
Eggs.
oil.
Okay, so we're making a cake with Dr. Henry. Dr. Henry does not accept oil. It has to be butter. Just let you know. Okay. What else?
Flour.
Milk.
Milk.
Flour. But we're gonna cheat because I'm lazy, right? And we're gonna use cake mix, exactly.
Egg.
Egg. That's right. She already got the egg part. Okay. What else?
Still. Oil.
Oil. Well, that's my butter.
Oh, that's your butter. Oh, you use butter instead of oil?
Yeah, we're gonna use butter instead of oil. It's got to be rich in butter, you know.
Milk.
Water. This is the hint. The hint for Dr. Henry's cake. You guys make my cake, you know.
Yeah, water.
Water. Okay, instead of water, let's use some milk. Right.
Yes.
Again, we want it rich, right? Okay, so that's pretty much it, right? There's nothing else, no special ingredients. Love, right? Love. Okay, how many eggs do you use?
3.
How much butter?
Half a cup.
A stick of butter, right?
I like half a cup. That sounds delicious. So a box of cake mix,
Mm-hmm.
and then how much milk?
Like a quarter.
A cup.
Quarter of a cup. Okay. Now, this guy is going to equal or yield 1 cake. Is that right? Is that true, or am I making it up?
Correct.
Okay,
Yes.
so guess what? This here is a chemical equation, right? 3 eggs,
Right.
right?
Yes.
It tells me how many eggs I need to sit there and do, right? How many eggs I needed to make this cake. It's half a cup of butter, right? 1 box cake and 1/4 cup of milk, okay? So that lets me know the quantity that I'm going to be using, okay? So when we're working with our chemical equation, it's exactly the same thing. We're just trying to get it balanced out so that we know that it makes 1 cake, right? Now, if we have 25 eggs, are we going to use all 25 eggs?
No.
No.
No, right? How many eggs are we going to use?
3.
3. We know if we use 25, it really messes up that cake. And we're making an omelet instead of a cake, right? With maybe a little bit of flour, right? Okay, so we want to sit there and think about it. I mean, really, when we're thinking about these chemical equations, all it is just a little recipe for us. But first, we got to get that recipe balanced out, okay? So here's the other thing. Some of you guys were putting, a -1 in front of, like, say we had N or O2. So I saw somebody put a -1. Okay, now logically, thinking about this, I have a box cake, right? I'm making a box cake. I'm not gonna add the box, the cake mix at all. So I'm gonna put a -1 here, right? Is it a cake?
No.
No.
So does it make sense to sit there and have a negative value for a coefficient?
No.
Because can you have a negative cup of butter?
No.
Is that what?
No.
Is that what's? You can't, right? And so you want to think logically, right? So there's certain things that you're like, okay, that doesn't make sense. Think about it. It doesn't make sense, right? In real life, if I'm making a recipe, I'm not going to have a negative of something, right?
Right.
Okay. Okay, so let's look at this chemical equation, right? Because all it is the same thing in this case. Only thing, all of the coefficients have been worked out under this circumstance. Okay, we have to work out those coefficients, right?
Yeah.
This part of the equation can't change. The only thing that can change are the coefficients in front. And so we need to keep track of the numbers. So how do we do that?
Start writing out like N and O.
Mommy.
Okay, so write down my elements that are in the
Yeah.
reaction, right?
Mm-hmm.
Okay. Now, there are certain rules that we always want to remember, right? We can't just magically, if it don't fit, we can't just magically put something over here and say, okay, I'm just going to put another O just because I want to, right? You can't do that, right? Once the chemical equation says that we have this, and it makes this, then that's it. You can't just magically add stuff. The only thing that we can change are the coefficients. And so that's going to be our limitation. So we have to make sure that we're changing the coefficients. We can't just magically add or subtract at our whim, right? And that's the law of conservation, right? So what we put in, we must get out, okay?
Okay.
Okay, so we know that we're putting in how many nitrogens
2.
right now?
2.
Hey, what chapter?
And then on the product side,
2.
okay, we know that we're putting in how many oxides?
4.
4.
And then on the, this is a typo. I was lazy. That should be 2. Okay, to make it challenging here. Okay, so, and then on the product side,
2.
now that there's 2. Okay, so now how do I balance it?
Putting the 2 in front of the
Oxygen.
oxygen.
Okay, so I put a 2 in front of the oxygen. But see, I saw a few people who were on there, they were actually doing it, and they went through the process. They said, okay, I have this many ends and this many, and they went through that whole process, and then they just did this. They said, okay, I need 2 here, so I'm just going to put +2. And then they called it a day. And they're like, okay, that's it. They didn't do any of the changes or anything like that. They put nothing up there, and then they left it as it was. So you want to account for everything. You want to make sure that you put, okay, I need 2 of these guys, right? Because that would give me a total of 4, right? And it's a multiplication, 2 times 2. So it's the coefficient multiplied by the subscript. That's how we account for things. So that's a balanced equation.
Yes.
We're good to go. Want to try something a little more challenging?
Yes.
Yes.
Sir.
Yeah,
Yes.
number 3 from the test.
Okay, so let's see. Let's do this one.
Can you throw a parenthesis in there?
I'll throw a parenthesis in there. That must be, I'm trying to remember. It'll come through. Yes, of course. Shikuria. Yes. I was like, she loves those parentheses.
I hate them and I forget how to do them.
Yeah, we'll do that one after this one. Okay. Looks sort of familiar.
They all look complicated.
Okay. So what do?
Write them out.
Write
Write 'em
down,
out.
Go.
write down the element.
Okay.
I have a question, Dr. Henry.
Yep.
On this one, on the NH4, that's one thing together, right? Or is that two separates?
Nope, that is one thing together.
Okay.
And then we'll start talking to you why it's written the way it's written. There's a special way that's it's written for a particular reason, but
Okay.
we'll get to that next week actually. So
Okay.
and then you guys will be like, oh, and then everything will start clicking. That's what we're hoping, or at least close to clicking.
Shoot, sorry. My bad.
Okay, so how many nitrogens do we have on the reactant side?
Two.
On the product side,
Two.
Two.
how many hydrogens?
4.
Four.
Four.
And on the product side,
2.
Two.
Two.
how many oxygens?
Four.
And product side,
3.
Three.
okay, is that balanced?
No.
No.
Okay, so what do I need to do to balance it?
Add a 2 in front of the H2O on the product side.
Okay, so we have a 2 in front of the H2O. So then that gives me how many hydrogens
4,
and how many oxygens?
4. No, 6.
Okay, is it balanced? Are you sure it's 6?
No.
Oh no, I'm sorry.
It's 4. 4.
It is four.
Okay, balanced?
Yes.
Yeah.
It
would be-
could be.
Right? And this is another thing that I wanted to point out because so I know a lot of you guys would put 0 here, but this is kind of understood 1. If there's nothing in front of it, it really means that there's a 1 in front. So it's like 1 times 2, right? Because then that would account for that 2 that we have. And then here, that's kind of like we don't put anything there, but we know it's understood to be a 1. Okay? So it's not really a 0, but it's really a 1. Okay? And then like that's the same thing with our subscripts, right? Here, since there's nothing here, we know that that means that there's 1. Like you guys, there's 1 here and there's 1 here. So these guys are kind of understood. When there's no number in front of it, it's understood to be 1. And I wanted to clarify that since.
Dr. Henry, so you know how we added the 2 in front of the H? We don't distribute to the oxygen too,
We do,
right next to
Right.
it?
It is.
we did, right? So it's 2 times H, which is 2 times 2. So that's 4 H's, right? And then 2 times our oxygen there. So then that's 2 oxygens. And then we had 2 oxygens that were here, right? 2 oxygens, right? So if we
Okay,
added those together,
confused. I thought we had to multiply like the 2 and the 2 again, and then the other 2, because I was getting 6. So we
Okay.
don't multiply the 2, only with the H.
yeah, because really what you're saying here, what this is really saying is that I have 1 water molecule, actually I have 2 water molecules. I have this water molecule and I have this water molecule. That's what that's saying, right? So then tell me, how many oxygens do I have here altogether? 2, right? And then how many hydrogens do I have altogether?
4.
4. So the coefficient is just letting me know how many of that molecule I have.
Oh,
Okay.
okay.
So, and since this guy, I only have 1 of these, right? Since it's understood to be 1, I only have 1 of these, and I only have 1 of these. Okay. So those are some of the mistakes that I saw on there. Some of you guys actually started out pretty well, and then you gave up on yourself, and so you just didn't put anything in there. And it was funny because I'm looking at it, I'm like, okay, they're on the right track. They put the letters down, and then they start looking at it, and they're like, well, okay, I'm just gonna give it up, you know? And so don't give up on yourself, try it out, you know? The only way you're gonna learn is by doing it. If you don't do it, you're never gonna learn it. And sometimes you gotta fail, you know? Sometimes you gotta fail really hard, and then it kind of wakes you up, and you're like, oh, okay, I got it, you know? Okay? So one more, and then we'll get started for today.
Can we make one of the
exam?
One of the, what was that?
Is because, well, these examples that you are providing to us, they are easy for me in some kind of team. And in the exam, in the question 2,
Uh-huh.
I have I'm sorry for my English. Partial?
Yeah, partial credit.
Yes, I would like to know why.
Okay, well, you
Can
can
you
talk to
make
me.
one of them?
Yeah, you can talk to me about partial credit because I did give you guys some partial credit. But there are some people that still, right now,
Okay.
because we've had some
Working on that.
issues with computers
Okay.
and things like that, have not completed the exam. So I can't go over the exam questions. These have been close to the exam, but they have not been exam questions.
Okay, I understand.
Okay, but we
Dr.
will.
Henry, can we
Yes.
do one that's like the fraction?
We can do, so we'll do that one after this one. Okay,
Okay, thank you.
no problem.
Is that really supposed to be a little O on the, by the P, Dr. Henry? Okay.
Must be a little by that P. So does this fit the parentheses requirement there? Okay. So first off, can you guys tell me what the P lowercase o is?
It's not potassium.
Polonium.
Polonium.
That's right. Okay. Okay, so we know that polonium, P lowercase o, that's why it's important that we use that uppercase and lowercase, and we make sure we distinguish between the two. Okay, so what do we need to do? I've shown you 2 ways of going about this. Can you guys remember the 2 ways?
Do it either
Group it or put it separate?
We can group it or do it separate. So things that are moving in groups, so this capital P lowercase o, polonium, you can see it over here. So that's moving as a group. Well, it's itself. We have chlorine and chlorine. We have this guy's called ammonium and ammonium. And we have phosphite and phosphite. So that PHO4 is phosphite. Okay. So we can write these guys like we did with just the individual letters. We can write these as units since they're moving as units. So we could have our PO3 we could have our NH4.
And it doesn't matter that the first one has like a little O versus the other one?
Yeah, it does, because they're not the same thing. The P little o is different than the P capital O. Right? This is polonium. This is phosphorus and oxygen with 3 oxygens.
Oh, okay.
Okay? So they're different, right? And so that's why it's important to make sure that we're distinguishing between them. And then the last one is just our polonium, the P little o. Okay? Do you guys see that?
Yes.
Anybody not see it? And that's the other thing. Here's an opportunity, right? Opportunity to sit there and speak your piece, because if only the people that are seeing it are talking and the people who aren't seeing it aren't talking, then I just assume that everybody gets it. And then I'm just going to keep moving.
Dr. Henry?
Yep.
So I know in like even on the practice exam, there was something similar kind of like this,
Yep.
but my issue was that on the reactant side, we had all these formulas, but on the product side, it was kind of sectioned off. Like it's say theoretically speaking, it's only NHCI, and there was like and then CL, sorry, and then I think PO was separate, and I had an issue with it because I was like, am I supposed to put it all together, or am I supposed to separate it all completely and try to figure it out? But I know that if I separated it, it would only make it more complicated for me, right?
Okay.
It would make it more difficult in a sense.
It could, yeah, it could. It really depends on under the context.
Yeah.
And so, but the key is, right? So since we see these guys, right? We see them as moving in unit, right? So you guys see that the PO is only over here, and the PO3, oh, it's the PO3 over here. So those guys are moving in groups, okay? So you want to separate it when you see things that are moving in groups. When you don't see it moving in groups, then you want to, in that case, you want to separate it individually. You understand what I'm saying?
Yes, thank you.
Okay, so.
So, Dr. Henry, sorry.
Yes.
So only if they're in parentheses and they have the little, like the NH4, it's in parentheses, and the P capital O is also in parentheses, we bring that number with it down?
Yeah, because this is as a unit. You guys, this guy's works as a unit, right?
Okay.
So, and then that means that we have 2 of these units, right? Here, this means that we have 3 of these units. Okay, so when I ask you how many, as I said, this guy's called phosphite. How many phosphites do I have on the reactant side?
3.
Do I have 3?
Oh.
Because remember, this is a whole unit. I have 1. That's right.
You have 1 PO3. Okay.
Yeah. And then
Have 12 hydrogen, or do you just have 4
Can you repeat
sets
that,
of
please?
3? 4 sets of 3 is 12, so I'm tripping. Never mind.
okay, so if we look over here, because we're just looking at this unit right here, there's nothing on the outside of it. It's not in parentheses or anything like that. So we know that this guy is working as a single unit. It's 1 unit. Okay, now when we look on the reactant side, how many of these units do I have?
2.
You have 6.
I have 2 of that unit. I have 2 of the PO3. Okay, so that's why that 2 is there. So let me know that there are 2 of these guys. Are you with me?
Yes.
Okay.
So at
So-
what point do you multiply the 3 and the 2?
At the only time that you'd multiply the 3 and the 2 is if we were doing them individually, right? Because then you'd multiply, because this really what this is saying, this is telling us that we have 2 units of this guy. So we have PO3 and we have PO3. So there's 2 units of them. So that's 1 compound that's working together all the time as a unit. And that's why we put in parentheses. Okay, so these guys are a unit. They're going to be together. Okay, and so they're traveling together. That's why they're traveling together, because they're going to be together. Does that make sense, Daisy?
Yeah.
Okay. So what about ammonium? That's this NH4. How many
Three.
ammoniums do I have on the reactant side?
3.
And on the product side?
1.
One.
Okay.
NH4 is the whatever the chemical, right?
2.
So it's not separate.
Okay, so we have 2 Cl, and then on the product side,
1.
and then the capital P, lowercase o,
1.
One.
and then on the product side,
3.
Three.
okay, is it balanced?
No.
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 Okay, so what do I need to do?
In front of
You
the
need to
PO,
balance them.
on the PO3, you have to add another one to it.
Okay,
Add
so
them
how
to-
do I do that?
Did you put
You
a
would
2 in front?
PO3.
Ah, so I put a 2 in front of this whole compound, right?
Mm-hmm. In front of the PO3.
No,
It
because
can't-
this is all one unit.
Oh, the NH, okay.
Okay, you got to remember, let me make it a little bit clearer. If there's not a plus between it, this is a unit. And so we have to put it in front of the compound, not just that unit.
Okay,
Not
so
just that part of
PO3 is going with the NH4.
Yes.
Well, that's
Okay.
just wrong. Just kidding.
So
Yeah.
you instead you should put a 3 on the product side on the NH4.
In the parentheses is that?
Okay, so let's do the numbers here. So if we put a 2 in front of this guy, how many NH4s do we have?
Yeah.
6.
We have a total of 6. Okay.
So that's when you would multiply it if there's a coefficient in front?
Yeah, so you multiply it and you multiply that number. Okay, so then that's a total of 6 here.
Mhm.
Okay, and then how many PO3s do we have?
2.
Okay, so now we have 2.
Oh, because of the outside of the parentheses.
Wait, I thought if you put a 2, then you would have to multiply the 2 times the 3.
No.
So wouldn't that be
this is
6?
This is a unit. Look what we have right here. We have this whole thing. This is kind of like, okay, so in this case, we can substitute this for X. PO3 is going to be equal to just X, right? So all I'm going to do is I'm just going to write this here. I'm going to write NH4 3, and this is just X. And then over here, this is going to be PO3 just X, because it's working as a unit. You're not breaking it up. It's together. Can you see that?
Mhm.
Right? Since we took the time to write it as a unit, we want to keep it as a unit.
Wait, what do you mean?
Yeah, this is the unit. Right?
Okay.
Yeah, that's the whole, no. he
So in
said
that case,
the PO.
thing as we're saying 2 times X. Okay, so that's X. So we know that there's a 2 here for this X, right? Do you see the similarities there?
Yes.
Okay.
So Dr. Henry, that subscript number 2 on the product side carries over with the.
That's right. So now we had 2 here and we have 2 here, so that balances out. So we're using the coefficient in front of it to account for the 2 phosphates or the phosphites. So PO3, right?
Okay.
Does that make sense?
Yeah.
You guys have that look. If it doesn't, we'll try to find out another way of showing you.
Okay, so my thought is, when you're looking at like not balancing it, when you're looking at the whole equation, you have the P little o Cl2, and then you have a plus. So that kind of signifies that PoCl2 is together, and then there's a plus, and then there's the next little batch that's together, and then
That is
there's that
correct.
line.
That's
Okay.
exactly it. So that's kind of like, okay, so that's the same thing like when we're talking about eggs, right? Because we got eggs, we got butter, we got the cake mix, so if somebody said egg cake mix, right? So then you would assume that that's something special called egg cake mix, right? It's a special
Yes.
type of thing, because that's what I would assume. I'm like, was that something I don't know of yet, you know? And so it's kind of that plus means like our and. It's this and this and this.
Okay.
Okay?
POCl2 is eggs.
Yeah. Okay. Okay, so now we got the PO3 balanced. Now what about the NH4? Can we get that guy balanced?
Do we add a 6 in front of the NH4 on the coefficient
Okay.
side?
On the
product
you mean
side,
on the product side?
Product
Put a
side.
6 here.
Yeah, I get those names confused.
Okay.
I do too.
Okay, so we got a 6 there.
Mhm.
So then now we have 6 of those. And then how many chlorines do we have?
So now we have
Six.
6.
We have 6. That's right.
Can we put a 2 in front of the POCl2 on
Will
the
that-
reaction side?
Would that balance it?
It'd be a 3. You have to
No,
put
it'd
a
be a
6
3.
in front of it.
We have 3 because you multiply it, right?
That's right.
Oh, I'm sorry. Yeah, because of the other, sorry. Yeah, 3.
Okay. So then now we have
6. Hold on.
and
Times 2, 6. Yeah, now we're balanced. There we go.
But
Okay.
now we're unbalanced for the PO. Oh, no.
No,
Never mind.
Yeah, I know. That's what I was looking at too.
Confusing. Ugh. Now it's fully balanced.
now it's fully balanced. Okay, do you guys see that?
Yeah.
Mhm.
Yes.
Yeah.
Yes.
Give
Yeah.
us a hard one.
That
A
was
hard
hard.
That was hard.
Okay, so, and we could do it the other way that we've done it in the past, where we break down each one individually. I'm just going to show you it just to be thorough.
Please.
So basically, when there's parentheses and they're in units like this, we could ignore like the subscripts, like how the hydrogen has a 4 added to it. We can kind of
No.
ignore that a
Well,
little
you're
bit.
not really ignoring it. You're just kind of putting it all together. So
Okay.
you're working it as a unit, but you're not really ignoring it because you take it into account because you're using it as units.
Well, if I give
As a
it my
group.
attention, I'm trying to say that there's 12 hydrogens, and then it like throws me completely off.
Yeah. Well, so then maybe you should just do it this way. I'm going to show you the other way of doing it, where you just do in each individual one.
The long way.
The longer way, yeah. You know, because the goal is not to throw you off. We want you to get to the right answer, right? So
Eventually.
the long way would be just using each one individually.
So, Dr. Henry, on any future test, if there is one where you don't have to put anything like in the on the product side, the PO3, we just enter a 1.
Yeah, yeah. So any future test, and I'll actually put that because, you know, I went back and if you put a 0 there or if you left it blank, I went back and I gave you those. And that's also why it's taking me so long to go and grade all the tests, because I'm literally going through, okay. You know, and then there's also one that I was doing and I did it on the back of on the back of paper. I did it with my head and I made a mistake. And so I'm like, oh, now I have to go back and fix that one number for all of them too.
Okay.
So under those circumstances, I'll leave you guys a little note for balancing equations. If it's understood to be a 1, if there's no number there, it's understood to be a 1. So put a 1.
I think I was overthinking it because I really spent like maybe 10-15 minutes, I think, on number 3 or on one of them where I assumed there had to be a number. So I just kept working it all the way and my numbers just kept getting bigger and bigger, but I don't think I obviously didn't get it right, but can we get points for overthinking and trying?
Same.
It was hard.
It was.
We're here for the points, like you said earlier.
Wait, are we not doing regular lecture today? We're not going over the Lewis structure?
No, we are doing regular lecture, but I'm trying to get us to a point where you guys need this. Whether you like it or not, you need to be able to balance equations. If you guys can't balance equations, you're pretty much screwed in chemistry. Put it, you know? because
Yeah.
that's kind of like our bread and butter. That's part of our bread and butter. Now, don't get me wrong, Lewis structures are going to be important and everything, but I want to make sure you guys got a grasp on this. And what we're going to do is going to that last, because we're almost done with chapter 11. We're going to be finishing up chapter 11, and then we're going to be going into chapters 12 and 13. Those guys are going to go much faster because then the pieces are going to start coming together. Okay.
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 Dr.
But
Henry,
I want to
did
make
you
sure
re-
that you guys got this.
Did you
What was that?
review this with the evening lecture or the earlier one?
I sure did. Yes. Yeah.
Okay.
So what I do to one lecture, I do to the other. And again, I'm doing this because I'm recognizing there is a huge gap. I want to make sure those gaps are being filled. I know we're not going as fast as we would like, because if it were up to me, we'd be finished with the book already, right? And then we'd all be going on vacation this week. So, but we're trying to make sure that everybody got a good grasp on it. Okay. And I want you guys to have a good foundation, because with a good foundation, all of the other chapters are going to go through very fast. But that's going to require you guys, helping me out a little bit. Okay. Okay. So patience, please. For those, I know some of you guys are like in third gear already, so we're trying to get everybody else in third gear. Okay, so the long way about this would be going through the same thing. So again, how many POs do we have on the reactant side?
We have 4.
One.
Capital P, lowercase o.
We have one.
Oh, sorry. Yes, 1.
Okay, and then on the product side,
3.
how many hydrogens do we have?
4.
3.
12.
3. So 12.
Yeah, because remember, this guy represents NH4 3 times,
Right.
right? So that's what that represents.
Oh.
You multiply 4 times 3. And that's how I have to do it.
1, 2, so that's what? That's 4, that's 8, that's 12.
12.
Okay. And then on the
3 times.
4.
Okay. Dang, I get it.
4.
okay, that's right. So on the on the product side, 4. Nitrogens
3.
on the
It's because he doesn't have CL then.
okay, and then on the product side,
1.
1.
phosphorus,
1.
and on the product side,
2.
No, 6. 3? 2? I thought
now
Ew,
again,
Two.
no, slow down. What is right next to the phosphorus?
1. 3.
Oxygen.
What is right next to the phosphorus?
Nothing.
A 1.
Okay, phosphorus is just P, right? This is understood to be a 1, right? So this guy is in parentheses. So this is saying we have PO3 2 times. So how many phosphorus do I have?
6.
2.
Okay, so let's try this again. How many? Because the subscript here pertains to the one it's right next to. It's not pertaining to both of them. It's only what it's next to. Kind of like we had over here, right? There's an N, there's an N, there's an N. How many are there? How many N's are there?
3. There's 1.
Then, okay, so then if I have 2 PO3s, how many P's do I have?
2.
2.
2. Okay, so don't distribute. If it's right next to it, there's no parentheses, right? If it's right next to it, it's saying that's only for the oxygen. That is not for the phosphorus.
Okay.
Does that make sense?
Yeah, just what it's touching.
Exactly, just what it's touching.
Okay.
Exactly. When there's a parentheses, it's touching both of them. Okay. Do you guys get that?
Yes.
Okay, so that's going to be the important part right there. Okay, so, or one of the important parts. Okay, so oxygens.
3.
3.
And then on the product side,
6.
6.
okay. So now it should be a piece of cake, right? So we start at the top. How do we make capital P, lowercase o, balanced?
Add a 3 in front of it.
3.
3.
So put a 3 here.
Yes.
No. Oh,
Yes.
yellow.
Okay.
Put a 3 in front of it.
So then that means that we have 3 of those. So that's balanced. 3 over here, 3 over there.
Go to chlorine now.
Wait, are we missing chlorine?
No, well, we're gonna get
Yeah, we
there.
are.
Oh, I'm sorry. You're right. We're missing chlorine. I got
Like, I'm tired, man. That's
I got
tired.
carried away. So how many chlorines do we have?
2.
2.
Okay.
But now
Initially
we
we have 2,
Yeah,
but
let's
now
do
we
it
have
again.
6, right?
Yeah.
Yeah.
Okay. So now we have 6 of those guys. And then on the reactant side, how many do you have?
1.
Okay. So now let's look at the hydrogen.
All right.
So I have 12 over here and I have 4 here.
Let's put a 3 in front of the NH.
NH.
So
Now
put
we
3
have
in front of
12.
here.
Yeah,
Okay,
now
so
we have
then that
12.
gives me 12.
Mm-hmm.
Let's balance nitrogen.
Okay, so then that means how many nitrogens do we have now?
3.
3.
Okay, let's balance chlorine.
And then how many chlorines do we have?
3.
3.
It's gonna be interesting.
Let's go to oxygen.
Okay, so let's see. Now we have the phosphorus.
Phosphorus, yeah.
So we have 2 on the product side and we have 1 on the reactant side. What do I need to do?
Add a 2 in front of the NH4PO3.
Okay, so I put a 2 here. So that means now I have
2.
2 phosphorus, right? So how many nitrogens do I have now?
6.
6.
I have 6, so that changes this number. How many hydrogens do I have now?
You have
24.
4.
Wow.
4.
24.
Too many.
Okay. And how many oxygens do I have?
2 times 3 is 6.
6.
Okay, so my oxygens are good, but my nitrogens aren't and my chlorines aren't.
And
So
your
what do I need to
hydrogen.
do now?
And your hydrogen.
So you added 2 in front of the CA?
Add a 2 in front of where?
No. Let's do the one on
3
the
to a
right.
6 on the product side,
The
I need to
nitrogen.
replace. I need to replace that 3 with the 6 now.
maybe.
Wait,
Okay.
wait. Yeah. Yeah, 6.
that equals
Perfect.
Okay, so we put a 6 there. And then
24.
that gives me how many? How
Yep.
many nitrogens?
6.
6.
How many hydrogens?
24.
24.
And then how many chlorines?
6.
Okay, is it balanced?
Yeah.
Yes, sir.
Piece of cake.
I feel like that's easier.
Okay. Okay, so.
No.
Okay, so we're gonna do this. 1, 2, 3, 5. And then we'll get to our lecture. Okay. How many carbons?
3.
3.
And product side?
1.
1.
Hydrogens.
6.
No, sorry.
Product side?
2.
2.
2.
Oxygens.
3.
Product side?
3.
3.
Okay, is it balanced?
No.
Okay, what do we need to do?
You need to balance it.
Hey, smart.
Add a 3 on the product side in front of the
Okay.
H2O.
3 in front of the H2O.
Yeah.
Okay.
Yeah. 6.
And then how many oxygens do I have now?
5.
Is it balanced?
No.
Oh.
Add a 3 in front of the CO2 on the product side.
Okay. Is it balanced?
No,
No.
because we gotta do 3, 6 oxygen now. 7 oxygen.
Dr. Henry, can we add a 3 in the carbon in front of the reactant? Like all the way.
You just want to put a 3 there?
Yeah.
But if I put a 3 there, that gives me 9 carbons. That gives me
Okay.
15. Do I want to
Oh,
do
yeah.
that?
No. How
What about that fraction?
9 oxygen.
The fraction, the 7/2.
7/2? Do I need to do that? How many oxygens do I have in this compound?
3.
3.
Yeah, 3.
Oxygens.
Oh,
I
you
have
have
You
2.
have 3.
in this compound alone, only in this compound,
1.
how many oxygens do I have?
1.
I have 1 oxygen, right? Okay, so if I only have 1 oxygen here,
So put a 3 in front of the O too.
okay, so if I put a 3 in front of the O2, then that gives me a total of how many?
7.
7.
Okay, so then that gives me my 7, right? Because that's 3 times 2, that would be 6. And then we have the 1 over here, so that's a total of 7. Does that make sense?
Yes.
But isn't there 9 oxygens on the product side?
Yes, Dr.
Yeah.
Henry.
3 times 2, 6,
sorry.
7.
No, she's right.
3 for
There's
2
9.
and 3
Yeah, so that's 6.
more.
She's right, she's right.
Yeah.
So we have 9 over here, right? Because there's 3 here.
6.
So then,
So let's. So 3.
Just put a 9/2
Or
on.
4. A 4.
No,
4
no,
times
no.
2 is 8, 9.
1.
okay.
Yep, it's
Yeah.
a 4, yeah.
There you go.
Good eye.
Yeah.
Who was that? Who was that caught that? Was that Ariana or Adriana?
It was other person before and later I saw.
Okay. Good eye. Good eye.
That's true, because that could get you messed up on a test.
Yeah?
Actually, I think that's what got me messed up on one of my problems. I didn't complete it because I didn't finish it like that.
Okay. Questions, concerns, Cash?
Yes, I have a question. Go back
Okay.
to the oxygen because I was still counting. How did we end up with 9? So it's 3 times 2 is 6.
Plus 3.
See, I get confused because I thought we don't distribute it. I thought we just keep it to the H2.
No, if the number,
we didn't.
okay, so again, Daisy, this is saying that there's 3 H2Os. That's what this says. Yeah, and then I want you to count each of the oxygens.
One, two, three.
1, 2, 3.
Maybe I need to write it like that.
Yeah, then
That's
write it
great.
like that. Yeah.
Yeah.
So
Okay.
I actually had a student, and that's how she did everything, and that's how she kept remembering that. You know.
Okay.
Okay. So again, the
Got it.
coefficient means that you have 3 copies of whatever compound that is. In this case. In this case, this coefficient is 3, so we'd have 3 CO2. Okay. This guy has 1 in front of it, so we only have this guy. This guy means we have 4 oxygen gases. Okay. Are you guys good so far?
Yes.
Yes.
Okay, so we were talking about Lewis dot structure, right? How many of you guys are confident in Lewis dot structures?
I'm somewhat confident. Yeah.
Okay.
Honestly, it's my favorite part.
Okay, so first I want to answer, there's a specific question that was sent to me earlier, right? Somebody, and we're talking about compounds. She's a little ahead of the game there. So she had sent me this. She had done a compound that had C, Cl, Cl, H, and H. Okay, so first off, I never showed you guys this, but remind me, I need to show you a really good, cute thing. We're gonna keep you guys a little bit longer, okay? Just to show you that. Okay, so first off, carbon can only have 4 things attached to it at most. 4. So we can't go beyond 4. So that's the first thing. And that's because that allows it to reach its octet. That means it's like a noble gas by having those 4 things attached. At the most, 4 things. So what we're gonna do is, in this case, we have 2 carbons. That means carbon likes to be in the middle, because I'm gonna say this, somebody might be offended, but I'm still gonna say it. Carbon's a whore, right? Carbon likes to have 4 things around it, right? It likes to try to make everybody else happy, but of course it wants to be happy too. So we're always gonna put carbon in the middle.
I think there was 4 H's on that one, wasn't there?
Was it
It was
4 H's? I can't remember
Yeah,
it was
it
4
was
H's or 4
It was
for
H4.
CL. Yeah.
And you had to put the 2 CLs on 1 carbon, and I could not get it.
Yeah. So, well, it doesn't have to necessarily be under 1 carbon. It actually could be on the other carbon. You could have 1 on 1 carbon, and you're right. Let's see, 1, 2, 3, 4, H.
But the question said to put both of the CLs onto 1 carbon.
So then that's fine. Then you know that you'll have 1 that would have an H. Because at most, you're going to have a carbon that's going to be shared, right, between the 2. So carbon is going to bond with the other carbon. You're going to have 3 H's around this carbon, and then you're going to have an H and Cl around this one. So then that's okay. So
Can you
once we start learning, what was that?
Can you remove the background, Dr. Henry?
Yeah, I
It's,
can.
I can't really see
Does that help?
Yeah, that's way better.
a little better, yeah.
No, it's not. It's definitely
Okay.
not better. I was just kidding.
Let me do this then. Hold on.
Like it's opaque, pretty much.
Hold on. Just relax.
CL and
There we go.
Oh, of course. I can't send it back.
Oh.
I'll just redraw it. It'll take me. Okay, so let me kind of explain this so that you guys can kind of get a little bit of a head start of what we're going to be doing next week. And your homework assignments, I believe it's 5 and 6. Kalinga, you guys is going to be pushed back to next week. Harnell, yours is going to be pushed back towards the end of the week when you guys get back. Okay, so now everybody wants to be like a noble gas. The way that you be like a noble gas is by having what we call our octet full, or basically that outer shell. Remember when we were talking about valence electrons and all that stuff? So in this case, you're trying to pack it in there so that you're getting to be just like one of the noble gases. You want 8 electrons around it. So right now, if you look at carbon, carbon has how many valence electrons? What is the, let me take it even.
4.
It has 4 valence electrons, right? So it would have how many dots in the Lewis dot
4.
structure? It would have 4
4.
dots. Okay, so it wants to be like a noble gas. To be like a noble gas, you have to have 8 electrons around you. Okay, so the way that you can have electrons around you is by either sharing electrons or taking electrons. Okay, or giving up electrons, right? So you could either give them all up. If you have none around you, you're going to be happy. Or if you have 8 around you, you're going to be happy. Okay, hydrogen, how many valence electrons does hydrogen have?
Just 1.
It has 1. The most hydrogen can hold is 2, because it's going to want to be like helium. Helium is a noble gas. It has 2 electrons around it, right? And so hydrogen wants to be like helium, so it wants to have 2 around it. So if hydrogen gives it 1, and carbon gives 1, so then that means that these guys, this line represents 2 electrons that are being shared. Okay?
Wait, Dr. Henry, so what does the double line mean? I thought the double line meant, hold on, I wrote it down. 2 lines, double bond,
Yeah,
goes for electrons?
yes, oops.
You're
sorry.
sharing twice.
Yeah, they're sharing a total of 4 electrons in the case of a double bond.
Okay.
See if I can get this to erase without.
You
Yeah,
said they're sharing double electrons?
No. I'm saying here, I'm trying to remove that 1 electron. Let me see if I can. No. Okay, so hydrogen has 1 valence electron, right? So it can share 1 electron. Carbon has 1, it has 4 valence electrons.
Yeah.
Right? So it's going to share 1 electron with this hydrogen, and so that represents a single bond between hydrogen and carbon. It's going to share another one with this hydrogen, and then that represents a single bond with this hydrogen. It's going to share another one with this hydrogen. That represents another single bond here. And then it's going to share between the other carbon, right? So that means there's 2 electrons here. That's 2, that's 4, that's 6, that's 8. So carbon has 8 around it. So carbon is happy because it wants to have 8 electrons around it. Are you with me?
Yeah.
Yeah.
Okay, chlorine. Chlorine is a halogen. It's 1 away from being a noble gas. It needs to gain 1 electron. So it has how many valence electrons?
7.
It has 7 valence electrons. Okay, so it just needs to get 1 more, right? So chlorine is here to get its 1 more. I got carried away with the dots around it. Sorry, I'm having trouble with the eraser since I made a white screen. Do this. There. Okay, so chlorine has 7 valence electrons around it. So it's going to share 1 electron with that carbon, right? Since we know that it's already sharing with this one. 1 here, we're going to share 1 here, and then this hydrogen is also going to share 1, right? So then that means, again, carbon has 12 around, it has 8 around it, 2, 4, 6, 8. Chlorine has 8 around it. That's 2, 4, 6, 8. This chlorine has 8 around it, 2, 4, 6, 8. And hydrogen has 2, just the 2. Okay, so everybody's happy. Everybody's like a noble gas. And so the reason why chemicals react is so that they can try to get stable, like the noble gases, have 8 electrons around them. Okay, does that make sense?
Mm-hmm.
Yes. So they have a real simple life, right? Your goal is to try to be like a noble gas, be like the Johnsons, okay? Because the Johnsons are stable, they're rich and happy, okay? And so you want to try to figure out ways to make them stable. And so the first thing is that we have to be able to do is to be able to recognize the Lewis dot structure, right? So we know that hydrogen had 1 valence electron around it. We know that chlorine has 7 valence electrons. And we know that carbon has 4 valence electrons. And this is only occurring when you're sharing electrons, not when you're taking or giving electrons. We'll talk about the taking and giving a little bit later, okay? Does that make sense?
Yeah.
Yeah? No, maybe?
Yeah.
Yes.
Okay, so don't worry, I'm going to give you more. But I want to make sure that we can understand how to get valence electrons, how to figure out our valence electrons. Okay, can I clear this? Everybody got it down?
Yes.
Yes.
Okay.
Yes.
Okay. Okay. I cannot. Okay, so when we're talking about valence electrons, again, we're talking about things that are going to have the electrons that are going to be available to react, right? So the whole purpose of us learning how to do the electron configuration is to try to determine those electrons that are going to be available for reactions. Okay, so you guys remember that this here represents our s orbital, and this guy over here represents our p orbital, right? So I'm going to show you a quick way of determining how we can figure out who's going to be reacting with this, right? So if we're talking about, let's say, oxygen, right? The quickest way is just to add up how many electrons it takes to get to oxygen just from the S and the P. We're not going to worry about these guys yet because these are transitional metals. And so all we're going to be looking at is just this orbital and that orbital. So what you're going to do is you're going to go to the same period as oxygen, and you're just going to count across 1, 2, 3, 4, 5, 6. Okay, so oxygen has 6 valence electrons. Those are the electrons it's going to use for reaction. Okay, now I'm going to show you another quick way, right? Everything that's in the same group is going to behave the same way. So they're going to have the same number of valence electrons. So selenium, how many valence electrons does selenium have?
4.
Selenium, not silicon. Selenium.
6 still?
It's in the same group. It's also going to have 6, right? So we're just going to go ahead. This is what we're looking at right here. So that's 1, 2, 3, 4, 5, 6. Okay. When they're in the same group, they're going to have the same number of valence electrons. Okay. Fluorine. How many valence electrons does fluorine have?
7.
7.
7.
Iodine. How many valence electrons does iodine have?
7.
7.
Carbon.
4.
4.
Silicon.
6. No.
6.
Four.
No, silicon has 4. 4.
Okay. Nitrogen.
5.
Okay. So that means that we have 5 electrons to work with when we're trying to bond. And again, our goal is to try to have 8 around us, right? If we're going to be sharing, right? Okay. So that's going to kind of set you guys up for these next set of things. Okay. But we got to finish some other stuff. So that's pretty easy, right?
Yes.
Are you feeling confident?
Mm-hmm.
Okay.
Just one question.
Yes.
My internet was going out. Why do we skip D when we're counting again?
What was that? Can you repeat it?
My internet was going out, so I couldn't hear why we're only using the S and the P.
Because the S and the P it's the outer shell. It represents the outer shell, right? And usually what you're using the electrons in the outer shell when you're trying to react. Everything else is kind of packed up. Okay.
So we'll never be asked how to get the valence electrons for iron. Hold on, Mia.
So the valence electrons for iron, you could be asked to get the valence electrons from iron, but you're not going to get asked in this class. Probably in general chemistry, yes. Right? Okay. And so right now, when we talk about valence electrons, we're talking about that whole octet, trying to fill that octet. These guys are kind of special cases. All of our transitional metals, they're special, right? And so they're a little more complicated, and so they're going to take a little more digging into. And we're not in that area yet. You guys are not there yet. Okay, but you will get asked the electron configuration for iron, right? So you want to be able to do that, but you're not going to be asked the number of valence electrons. Okay. Does that make sense?
Yes.
Yes.
Okay. So let me see. I know it's kind of like working backwards, right? We already talked about this. Okay, so we already talked about Lewis dot structures. You guys are feeling pretty confident with your Lewis dot structure?
Yes.
Okay, good. Okay, so now we're going to talk about trends. So the periodic table gives us a lot of trends, okay? And I'm going to share those trends and we're going to go over it pretty fast. And so, but I want you to try to remember it as much as possible. And things will start kind of making sense if you kind of listen and kind of pay attention, okay? So in terms of the atomic size or the atom, the size of the atom, how big the atom is, right? So the trend is, as we go from left to right, the atom is going to get smaller. And then as we go from top to bottom, the atom is going to get bigger. Now, the reason why it gets bigger is because, remember the Russian doll theory, right? So here, level 1 is like right here, and then level 2 is we're putting it right on the outside. Level 3 is putting it on the outside, and so on and so forth. So you're just making it bigger and bigger and bigger each time you go to each of these periods, okay? So it's going to get bigger as we go down, and it's going to get smaller as we go from left to right, okay? So the reason why it gets smaller from going left to right is because you have more and more protons in the middle of the atom. And so those protons are going to be pulling those electrons closer to it. Okay, so I'm going to ask you a really hard question. Knowing that, who is bigger? Who is the biggest atom on the periodic table?
Franklin.
Radium.
I didn't say that right.
What was that?
Francium.
Francium? So francium would be the
Francium, there
biggest.
we go.
Yes, francium would be the biggest. Radium would be the next biggest, right?
Oh, okay.
Okay, so if we're going from, who's going to be the smallest, the absolutely smallest?
Hydrogen.
Helium.
Helium?
Helium, that's right. Helium is going to be the smallest.
Okay. It has
Okay.
nothing to do with weight. It's not the atomic weight. It's just
No,
where it
it's
lays on the
size.
table.
We're talking about size.
Okay.
Right? So, you see some people, they're really fit and everything like that, and they get on the scale, and they're like, man, that guy weighs a whole lot, considering how small he is, right? Because he's all muscle, right? So you can't judge it by its weight. It's based upon size, okay? So when we're talking about size, we're talking about size. When we're talking about weight, we're talking about weight, okay?
Okay.
Okay, so let's see those skills. So here's the question.
They're going to be on the test.
You're going to have a question like this on the test. You're always going to have a question like this on the test.
All right.
I'm not going to say this is the exact question you're going to have on the test, but you're going to have a question like it. Refer to the atomic table and list the atomic numbers 15, 16, and 33 in order of increasing atomic size. Okay? So in other words, look at our periodic table and let me know who's bigger, 15, 16, or 33.
33.
33.
Okay, so 33 is going to be our biggest. Okay, so then who's going to be the next? So
Phosphorus. P.
okay, so then that's 15. Okay, so phosphorus. And this is arsenic. Okay, and then who's going to be the smallest?
16, sulfur.
Simple?
Yeah.
Okay.
So we're going to need to know how to write it.
Yeah. You should be able to write it, right? Pac-Man. Oh, you guys don't know who Pac-Man is. But some of you guys might. People who play the lottery does. Pac-Man eats the bigger number.
Huh.
What about Mrs. Pac-Man? What is she?
Mrs. Pac-Man eats a bigger number too. Okay. Okay.
Can you explain that one more time, Dr. Henry?
What do you mean?
About the how you went from 15, 16,
Okay.
and which one was the smallest one?
Because look at, no, I want you to explain it to me. Look at what the table said. So as we go from left to right, it gets smaller. As we go from top to bottom, it gets bigger, right? So we're looking at atomic numbers, 15, 16, and 33. Who's going to be the biggest?
33.
33. Because is it?
It's going down
33?
and it's going
It's
big.
going exactly.
Yeah.
Yep.
Mhm.
Okay.
Okay.
And then
Okay.
who's going to be bigger between 15 and 16?
16's gonna be big. No, 15's gonna be bigger because it's going from the smallest would be 16, right?
That's right.
Okay. Okay. Got it.
Can we
Okay.
just have a bunch of those on the test?
I'm not going to give you those exact ones, but I'll give you something.
Those are easy. The other ones are hard.
You always say that. Yeah, it's easy after we go over it, right? And then, but the thing is that you need to be able to figure it out, right? So we're going to give you some other ones just to check it out. Okay, so I want to know who's going to be bigger. The biggest, we want to go the smallest to the biggest. Let's do 27, 33, and 15.
15's the smallest.
Okay.
27's the
And
big.
then 27.
So 27's the biggest.
33 is the smallest, and then 27's the
Mhm,
biggest.
27's next. So 15, 27, 33, and then 27.
15, 33, and 27?
3 and 27. Yes.
Okay.
So we're writing smallest first, and I was going
Yes.
backwards.
No, we did it the same way the last time. Pac-Man eats the bigger number, right? So 15 is smaller than 33. 33 is smaller than 27.
Okay, got it.
You always think I'm trying to trick you.
Because I was writing 27 first, and you guys were going 15 first, you know?
Yes.
So I was going the opposite, which I was saying 27 is bigger, but I was going like how you wrote it the first time, and then you went
So-
the other way.
How, because I was doing it that same way. So if our arrows are, going in the right direction, saying that the
Yeah.
33 was greater than
Although
27
the
was
question, you have to read what the question asked. The question says
Oh.
an increased order of increasing size, right?
Oh, okay.
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 Dr. Henry, what if the two elements you give us are diagonal from each other? Like, let's take example, aluminum and carbon. Which one would be bigger?
Aluminum.
Aluminum would be bigger.
Aluminum would be bigger.
Yes,
Furthest in the
aluminum would be
left.
bigger because it's in another energy shell. So it's kind of like it has that next layer of electrons. Does that make sense?
Yeah.
Okay, let's see. I know we're running over, but it's important. Okay, so ionization energy. Ionization energy is the energy that it is required to remove an electron. So first ionization energy is the energy that's going to be required to move one electron from an atom, okay? And then second ionization energy is the energy that's required to remove an electron from an atom that's already lost one electron. And then third ionization energy is the energy required to remove an electron from an atom that has lost two electrons already. Okay, does that make sense? Okay, So this is an example. So this
Doesn't
here,
make sense to some
Doesn't make
people.
sense, sorry. I'm like, no.
Some people are shaking their heads.
okay, that's good. That's why I'm showing the picture right here, right? So here's an atom, right? Ionization energy is the energy that's required to take away this electron right here. We're going to take it away from it, okay? So there's a certain amount of energy that's going to be required to remove an electron. Some of them, it's energy just to get over the hump. Some of them, it's like, it's a lot of energy, okay? And I'll show you that here in a second. Does that make sense? Yeah?
Yes.
No, maybe? Okay, so
Okay.
we're just taking away that electron. There's energy that's going to be required to take away an electron, okay? So now, second ionization energy would be the energy that's going to be required to take away the very next electron after we've already taken one away from it. So first ionization energy, second ionization energy would be the one that's required to take away this electron, one of these electrons that are in this p shell. So then it would be 1s2, 2s2, 2p5. Okay, and it would be Na2+. So that would be our second ionization energy. And that would take a lot of energy for this case. Okay.
Is it 2 plus? Is it 2 plus because you took 2 away?
That's right, because we took one away from in the first ionization energy, and then this would be for the second ionization energy, right? So then that's the reason why it would be 2 plus.
Because
So
it
when we
makes
went
it
from-
positive. Is
That's
that right?
That's
Okay.
right. It would make it positive. That's right. Each time you remove an electron, you have more protons, and so it's going to be positive.
Okay.
Okay. Okay. And so if I want the third ionization energy, that would be trying to make it Na3+, right? So that means I'm going to take one more electron away in that case for the third ionization. So that would be 2s, 2p4, and we've gotten rid of another. Right? Now, the thing is, to do this, right? Certain electrons are going to be like, yeah, you can take this electron. It's fine. It's not going to take you too much energy. I want to get rid of it. And other ones are going to be like, no, you are not taking my electron. So they're going to kind of fight you for it, right? So the ones that are going to fight you for it are going to have higher ionization energy. Okay. So let me show you this on the periodic table. Maybe. Okay, so for first ionization energy, so if I click here, this is our scale, and this tells you minimal, maximal. So this is increasing. So as we go from left to right, it's going to increase in first ionization energy. As we go from top to bottom, it's going to decrease. And if you notice, the numbers here have changed. This represents the ionization energy, right? And you guys can see there are going to be some exceptions. There's always some exceptions to everything, particularly nitrogen. Nitrogen loves to be an exception, right? But the general trend is it gets smaller as we go down, right? Generally. And then it gets more increase as we go from left to right for the first ionization energy, okay? So that means that atoms like lithium, all the way down to francium, these guys, it's going to be easier to sit there and remove an electron from these guys than it would be to remove electrons from helium, right? Because helium is stable. Helium does not want to be, don't mess with it, right? So it's going to be really strong. You cannot take an electron, okay? So it's going to take a lot of energy to do it. So it's kind of like here, these are those unfit mothers that are like, oh, they just let their kids play out in the streets and everything like that. And then, oh, you know, their kid don't come home. They haven't even noticed, right? And these are those moms that are there, it's their very first child, and they have their kid right next to them all the time, right? Which one is going to be easier to take a kid from?
The unfit.
The unfit mother.
Right? So you just got to be able to pluck it. So, you know, these are kind of like these moms here, particularly, they have 50 kids, and they're like, oh, you take one. You can take it. You can hold it. It's yours, right? So
They won't even notice it's gone.
yeah. So, and that's exactly what's going to happen, because these guys, as we go down, we have more and more and more electrons. So these guys are kind of like those mothers that have like 20 kids and, you know, stuff like that. You know, so they don't even notice, like you said, they don't even notice that they're gone. Oops, I lost a kid. You know,
I'll make another one.
yeah, exactly. Where this is like, I have one kid and they're holding on to it like all together, right? And they're like, no, you can't have it. That's my kid. That's my child. Okay. So does that make sense?
Mm-hmm. Yes.
Yeah.
Okay, good.
I had a question though, Dr. Henry.
Yep.
When you take away those two, where do they go? Because they're still somewhere.
Yeah, well, so you're right. They're being taken away. And usually the only time that they ever get taken away is if somebody else wants them. Like these guys here are going to want electrons, right? And that's called electron affinity.
Okay.
Affinity, like if you have an affinity for something, that means you want it, right? You want it. These guys are going to have high electron affinity, meaning that they're going to want electrons. And these guys are going to have low ionization energy, meaning that they're going to want to get rid of an electron.
Okay.
So remember when I told you, I said there's 3 ways to become stable, right? So either you can take, you can give, or you can share. Okay. So sharing is what we talked about earlier, covalent bonds. Taking or giving are going to be ionic bonds. Okay.
Okay.
So, but that's actually a good question, right? And it's a dynamic process, right? So one is going to be taking, one is going to be giving.
Okay, wait, you said take and give is ionic, and then sharing is what?
It's covalent.
Covalent. Thank you.
Okay.
Dr. Henry, did you want us to print periodic table of this green one?
You can if you want to. If on the exam, what I'm going to do, I'm trying to set it up so that you guys will have access to P table on your exam.
Yay.
So then all you need to do is be able to use P table. Okay.
So we can't use our own paper one or no?
You can use your own paper one. That's fine.
Okay, good.
Oh, okay, because I have mine and mine's written all over it. So I can see what I'm doing, you know?
Okay,
Not like
so-
cheating, but I mean like I kind of highlighted already like where the P, where the S is. And just
That's what they all say. It's not cheating.
No, I'll
I just
show
have
it to
all
you.
the right answers there and everything like that.
I have all the numbers of the valence electrons for each column. I have those all marked.
Okay. Okay, so this is just basically showing you that trend of ionization energy, particularly the first ionization energy. This is just telling you what I just told you about the second ionization energy and the third ionization energy. And then this is just proving that true. Okay.
Okay, another question, Dr. Henry, sorry.
That's all right.
So when you go from one, you take the one away, and then
Yep.
you go to the next step, and you're trying to take another one away. So you need this other energy to take it away.
That's right.
Is it a higher energy that's needed to
Yes.
take it away?
Yes,
Okay.
it is. So here's the first ionization energy. If you click down here and go to the second ionization energy, look at lithium, because these guys only wanted to get rid of one electron. And then for it to take another one, you have to put a lot of energy in it, a whole lot of energy. They're like, no, you cannot have it. I am a noble gas now, because lithium, if we look, remember, lithium is Li, right? How many valence electrons does lithium have?
One.
One.
It has one, right? So once you get lithium rid of that one, it becomes Li plus, right? And then it's like, oh, what? Guess what, dude? I'm a noble gas now, right? I'm just like, I'm just like helium. Right? So then he's like, I'm good, right? And then you come and say, hey, I'm taking your electron. He's like, no, you are not taking my electron. I worked too damn hard to get like this, right? No, you're not doing that, right? Okay, so does that make sense?
Yeah. It does.
Okay, but that's actually a very good question. Okay, and then if we wanted to look at the third, ionization energy, just go ahead and click P table, and you guys can see these guys can lose 2 electrons, and then after they lose 2 electrons, they're like, nope, you cannot have my electrons. There's no way. No, you can't, you know? Okay. Okay, so there's a couple of other things that we want to go over, but I want to ask this question first. So knowing what you guys know, can you guys put this in order? The beryllium, nitrogen, and fluorine in order of increasing ionization energy.
Can you show us the periodic table here?
I sure can.
And
Let's see, maybe. Oops. There we go. So we have beryllium, nitrogen, and fluorine.
In increasing order of what?
Of ionization energy.
so would fluorine be?
Ionization energy.
Fluorine.
What was that?
Fluorine would be first, right? Because it has more.
Okay. In terms of increasing ionization energy, who's going to have the lowest ionization energy?
It would be beryllium.
Be beryllium.
Beryllium, right?
Yeah.
And then?
And then it would be nitrogen, right?
Okay. And then it would be?
Fluorine.
Okay. Right?
Is
Because
it because
it increases from left to right.
but fluoride would be, oh, never mind. I never mind.
Since it increases from left to right, that means fluorine is the heaviest, right?
Not the heaviest. We're talking about ionization energy.
Increase.
Yes. So in other words, fluorine is like, no, you are not taking my electron. We will fight for this electron. Right?
You're not taking my child.
Yeah, exactly. Where beryllium is like, okay, yeah, sure, you can have it, you know. You don't have to fight it too much, you know.
So when we learned the stuff with the Pac-Man, would fluorine be the smallest?
In terms of, you're talking about the atomic size?
Atomic size, okay.
Yes.
Then fluorine is smallest, okay.
Yes. Yes, fluorine is the smallest in that case of these three. Yes. Okay. Okay. Let's see. Where did I go?
Can you do another one of those, but with different ones?
Sure.
We're on the same, you know.
Okay. Let's see. Let's do. Okay, so let's do phosphorus, arsenic, and calcium.
Calcium.
Are we doing circle them to largest?
So we're going from smallest
ionization.
Oh, okay.
smallest ionization energy to the largest ionization.
Oh, never mind. I found them all.
So it's this guy.
The calcium is
this
the calcium has less fight, you know.
Okay. So calcium.
So then that means that
Okay, and
and
then
then phosphorus would be next, right? Phosphorus?
would
I'll say
it?
arsenic.
Oh no, because it's lower. Yeah, you're right.
Yeah.
It is. It's arsenic. Sorry.
And then phosphorus.
And then
phosphorus. Because
Give
it's
us
on top.
another one. Another one.
Yeah, another one.
Okay, so this last
DJ
one
Khaled
is
one.
more stuff. And we're already over. I know you
Give
guys
us
are
a
excited.
juicy one, a juicy one.
Okay, so let's see. We'll do. Let's do.
Peanut butter.
Dr. Henry?
Yep.
So why would arsenic be before phosphorus? I thought the ionization energy decreased from top to bottom.
So as we go, you said ionization energy decreases from top
to bottom.
to bottom, right? Okay, who's on top?
Phosphorus.
Phosphorus. And then so that means that who's lower in ionization energy? Phosphorus or arsenic?
Arsenic?
So you just answer your question. Right? So
It's because it decreases, right? Because it decreases as you're
going down, right?
Going down, yeah.
Yeah. So that means arsenic is lower than phosphorus. Phosphorus has the highest. Remember, Pac-Man eats the bigger guy.
Oh, okay, I'm reading it wrong. Thank you.
No problem.
So,
Okay, so we have rubidium, strontium, and palladium.
What's rubidium?
Rubidium
Would be first.
Rubidium would be the first one.
Then
And then strontium, and then gallium.
And then it would be, yeah. How do you say it?
Gallium.
Gallium.
Good job. That's
So
it.
you put it in this. You put it in the correct order.
Yep.
Basically for us.
I
You're
was
supposed to
just trying
make
to
it
throw you off.
challenging. Gotta make it challenging, Dr. Henry.
That was challenging, you know, because you guys weren't expecting it to be in that order.
That's true. Let's move on.
We had to find those. Those aren't the normal ones that we already have memorized as to where they are.
Yep. Okay, so groups, when we talk about groups, group one is alkali metals, right? So groups are going to behave similarly, right? In terms of how they react and things like that. So because they have one valence electron, they're all going to kind of behave very similar, right? The only one that's going to be a little bit different is hydrogen. Hydrogen is kind of weird. Under certain circumstances, it'll act like those guys, but other times it doesn't, okay? So these guys are very reactive metals. So if you expose them to the air, they kind of ignite. If you expose them to water, they kind of ignite. So they're very volatile. They want to react because they want to get rid of that one electron. So they're anxious to, okay, let's go, let's react, you know? So the halogens, which are on the other side, I'll show you that on the periodic table. The halogens are also very volatile, right? They want to react as well because they are only one away from being a noble gas. So they're going to be very reactive. These guys are only one away from being a noble gas. So they're going to be very reactive, okay? And
Can you use your pointer, Dr. Henry?
yes. Thank you. I keep forgetting about that. So the alkali metals, those guys are just one away from being a noble gas. So they're going to be very reactive. They want to react. Halogens. These guys are halogens right here. So it says up here, halogen, right? So these guys are going to want to react as well. Okay. So because they're both, these guys are one away from being a noble gas. They need to gain one electron. These guys, they need to lose one electron. Okay. Clear. Okay, so this is just basically showing you that they're very reactive. And you guys can see it's already steaming and everything just by the addition of water. So these guys really want to react. This one is just, again, the addition of water. Get a nice spark. Here we have potassium, just the addition of water. These guys are the chlorines by the addition of phosphorus. Get these beautiful reactions that go on. Okay.
So is it like how people make drugs?
What was that?
Is it kind of like how people make the drugs? Like, you know, when you gotta, you know, it's reacted.
Well, yeah, I mean, chemical reactions are essentially that. You know, you're adding two things and you're going to get something out of it, right?
I wouldn't recommend.
Or not, you guys do that a lot too, right? So, for instance, well, you're not supposed to, but if you guys add bleach and ammonia together, right?
Knock
That's
somebody
toxic,
out.
right? Yeah. And so that's, what is it called? Something gas.
It's not yellow mustard. No.
Mustard gas. Thank you. Mustard gas. It actually, and if you're in a closed room, I mean, a lot of people who are cleaning houses and stuff like that, or in hotels, that would happen to them quite a bit in those hotel rooms. They'd mix the two together, and then they'd find out later on they'd find out that they're dead because mustard gas, right?
Yeah.
They just basically made mustard gas and killed themselves. Okay.
So what is it? So we don't do it at home? It's bleach and what?
And ammonia.
Oh.
Look on TikTok.
Oh God.
Okay, so we've talked about the alkaline metals. We've talked about the alkaline metals. The alkaline metals, they're reactive too, but not as reactive as the other. And then the transitional metals, they're not as reactive. We have halogens, we have our noble gases, we have the halogens, we have the picogens, or I'm sorry, the nicogens. And then, so these guys, you know, they have their groups. Those that are in the same group are going to behave very similarly. So if I say, if I ask you, which element is going to behave similar to oxygen in a reaction?
Nitrogen. Mm-hmm.
Oxygen.
Oh, oxygen.
Sulfur. Which sulfur, right? Because it's in the same group. So things that are in the same groups are up here. This is groups, right? These are periods.
Okay.
Nitrogen is in the same period. Nitrogen and oxygen don't behave the same. So who's going to behave like nitrogen?
Sulfur.
Phosphorus. Phosphorus is going to behave like nitrogen. Who's going to behave like silicon?
Carbon.
Carbon. Going to behave like aluminum.
Boron.
Who's going to behave like strontium?
Calcium.
Calcium, yeah.
Oh, strontium.
Okay.
So it can be any in that same row, right?
Yeah, it can be any in that same group. Yes. So groups are like chemical families, right? And so.
So when we're talking about the group, we're talking about the same column, not like the color, like the reactant.
That's right. We're talking about the same column. We're talking about, because remember, these are our groups. This is group 1. This is group 2.
Oh,
right?
okay.
So these are groups up here. These are periods right here. Okay.
Same column, not the row.
That's right. Okay. Okay, let's see. Okay, so we all know about the noble gases. The noble gases are in what group?
18.
18. Yeah, that's right. Noble gases are in 18. They're stable. Everybody wants to be like, right? We know that they're non-metals. They're not metals. We also know that they're not halogens, right? They don't want to react. If they're given a choice, they don't want to react. Okay. Make sense?
Mm-hmm.
Yeah.
Yes.
Okay, so you want to be familiar with metals, right? We know metals have certain properties. Metals are lustrous, meaning they're shiny. They're ductile, meaning we can sit there and stretch them into wire. They're malleable. We can kind of flip them over and bend them and stuff like that. They're good at conducting electricity. They're good at conducting heat, right? So that's why we use metals to cook stuff, right? Metals are going to want to lose electrons. They want to get rid of them, right? And metallic characteristics are going to increase from right to left. And I'll show you that here in a second. And it makes sense. Non-metals are going to be brittle. They're going to be dull looking. They're going to be horrible at conducting electricity and horrible at conducting heat. So we use a lot of non-metals like plastics, right? Because all that is carbon and hydrogen. So all of those, both of those are non-metals to sit there and insulate things, right? And then metalloids they're between metals and non-metals. So they have both characteristics of metals and non-metals. Metalloids do, okay?
Mm-hmm.
And this here basically tells you the characteristics of metals and non-metals, all the things that we just kind of list. So you want to be familiar with this because I love asking you questions like this because these things are going to kind of be important later on. And when we decide to do reactions, you'll be like, okay, so should I use a metal prong to stick into the light socket?
No.
No, why not?
That has
It has electricity.
Because it conducts electricity. So if you're holding a piece of metal and you stick it into a light socket, what happens?
Yeah, fry yourself.
Okay, you fry yourself, right? So, okay. So this is just basically showing you the general idea of metals, but we have like a table that does it so much better. If you click up here, it shows you all the metals, right? You click here, shows you the metalloids. If you click here, it shows you all the non-metals. You guys see that? Or am I?
I see it.
Yep. I love P-table. Okay. So let's see. Can you guys see my screen? Okay. So metallic characteristics increases from right to left, right? And it also increases from top to bottom. Okay. So it makes sense if you think about it. Where are all the non-metals? Which side are they located at? On the right side or on the left?
On the left.
On the right.
Non-metals.
You said all metals?
I said non-metals. Where
Oh,
are
on
all
the
the
non-metals.
non-metals?
Oh, okay.
Right.
On the right-hand side.
They're right here, right?
Yeah.
So wouldn't it make sense? Because all of the other metals, everything else is going to be metals, and we're going in this direction, right?
Yeah.
So metallic characteristic is going to go from right to left.
Aluminum is way up high on that chart, but it's got all is it a metalloid?
No, aluminum is it's called a post-transitional metal. It is a metal.
Oh, because it's way up there. It's not with the other metals.
Well, because if you look at my screen, so these guys here, all of these guys in blue, those guys are called post-transitional metals.
Okay.
Okay. These guys are your metalloids.
Okay.
There's a bracket too that says metal, and then the post-transitional metals fall within that whole bracket.
Yeah.
So it's part of metals.
And if you just click here, this tells you all of the metals.
Yeah.
Okay.
Okay. Okay, questions, concerns, Cash. Okay, that's chapter 11. Okay, and you guys have gotten a little glimpse of chapter 12 when we were talking about the fluid structures. Okay, we'll go more into that. Chapter 12 is really quick. We're going to do chapter 12 in probably like 30 minutes on